should be recording now.
Right away. Okay.
All right, so let me introduce our speaker. So we're delighted to have Moira Dillon, who is an assistant professor of psychology at New York University. She received her PhD from Harvard University, and she's a recipient of the National Science Foundation Career Award for her work on the cognitive origins of geometry and its implications for both formal and informal learning. Dillon was also named a Rising Star by the Association for Psychological Science for her work characterizing infant and machine intelligence. Dillon collaborates with the National Museum of Mathematics in New York City to pioneer innovative programming at the intersection of cognitive science and mathematics, and she partners with economists, educators, and policy designers to design, test, and scale game-based curricula for school readiness in mathematics. Dillon's research everywhere aims to show how human knowledge can be accessed to improve learning across diverse contexts. Thank you so much for joining us. We're delighted to hear you speak, and feel free to get started.
Great, thank you so much. And hopefully everyone can see my slides okay and hear me okay. Maybe just a thumbs up. Yes. Let's see, I got the chat here. I'm trying to hold these meeting controls. Okay, lots of thumbs up. Great, thank you so much. I'm gonna hide these again. Awesome, well, thank you for the invitation and the introduction. I am excited to share my work with everyone today. The title of what I will present is Becoming Euclid, Characterizing the Geometric Intuitions that Support Formal Learning in Mathematics. So I'll start by just broadly introducing the sensitivities that we have to geometry in the everyday world around us. And sensitivity to geometry of the external world is evolutionarily ancient. It's shared by humans with diverse species. So rats, zebrafish, even newly hatched chickens have abilities to navigate places and recognize the shapes of objects in ways that are strikingly similar to those of young children. Nevertheless, and importantly, these two abilities in us and in other animal species as well are dissociated. The way that we navigate places and recognize object shapes are two different ways that they rely on different geometries. So when we navigate places, we tend to keep track of the allocentric distances and directions of the environment's boundaries. So how far away we are from the extended surface features in the environment and whether we need to turn left or right, for example. But when recognizing object shapes, in contrast, it matters less how far away something is or what direction it's facing, but rather, as long as it has the right shape, then we can recognize it as the particular object that we're looking for. So there are these dissociable abilities for navigating places based on geometry like distance and direction, and on the other hand, recognizing objects by their shapes. These are abilities that we humans have from very early in development, and they're phylogenetically ancient. We share them with other animal species. They're not uniquely ours. But today what I want to focus on is how this foundational geometry that we use in our everyday lives and that other animals use in their everyday lives too, the geometry to interact with physical scenes and objects, can nevertheless support our human cultural flourishing in mathematics, in particular in geometry. And this world of geometry is not physical and concrete, it's abstract. There's a spatial world of zero-dimensional points, infinitely long lines, and endless planes. And these are abstract entities that we ask children to learn in school, but they're not things that we really ever experience directly in everyday life. We experience the physical scenes and objects of everyday life. So how does this kind of learning in geometry and about the abstractions of geometry, how does it happen? And on what foundations are these abstract conceptions built? So since antiquity, our capacity for abstract geometry has often been held up by philosophers and scientists as the model of human abstract thought. And so I'm hoping that the work I'll show today might inform not only the way that we think about the cognitive foundations of this a great achievement that we're able to make as learners, but also philosophical debates about the origin of geometry, and even geometry pedagogies that aim to address socioeconomic disparities and further human achievement. And what I'm going to propose is that our uniquely human capacity for abstract geometric intuitions relies on the same foundational geometry that humans and non-humans animals use to represent the physical spatial world. So abilities for navigation and object shape recognition. And I also want to note that I'm going to suggest that this doesn't require any actual navigation or object recognition, that there is enough in our capacity for simulating these processes that will then support our reasoning. So to give an overarching sort of framework for where the theory that I'm going to suggest fits into some of the other proposals for the cognitive origins of geometry, I'm gonna lay out three of them. So one possible theory for the origins of human geometry is that we possess an early emerging and abstract representation of Euclidean principles, things like concepts of linearity, parallelism, perpendicularity. And these get composed in an algorithmic-like language of thought for geometry. And like I said, these are really the kinds of foundational concepts that you might see in Euclid's Elements. And they're represented as symbolic concepts. So they can be composed into different instructions for how to make a form. So for example, you could compose 4 right angles into making a square. And the evidence for this proposal has come from cross-species, cross-cultural, and computational work using primarily an oddball paradigm that presents participants with an array of planar figures like squares, parallelograms, and trapezoids, and then asks participants to find one figure in this array of 6 that is the oddball, that doesn't belong with the rest. And the idea is that the more Euclidean the principles exemplified by the context figures or the deviant figure, the easier it is for a participant, a human adult and child, to find that odd shape. So the more regular that shape is, according to the principles of Euclidean geometry, the easier it is for human adults and children across cultures to find that shape. But this is not the case for baboons, for example. So the idea is that this is this regularity in shape as defined by these particular principles is something that pops out almost to humans uniquely. And this is not only true for humans versus other primates like baboons, it also seems to be true for computational models of geometric discrimination as well, where the state-of-the-art convolutional neural networks, for example, aren't able to capture human performance, either adult or child performance, on a task like this, but rather they look more like baboons. And only a model that includes a symbolic list of discrete geometric properties can perform like humans. So the second proposal for cognitive origin of geometry is it's an appeal to these evolutionarily ancient and dissociable geometric systems, as I had previously described, one for navigation and another one for 3D shape analysis and 2D shape analysis. That allows us to recognize objects. And this proposal suggests that the system dedicated to navigation, which prioritizes distance and direction, can combine with a system of form analysis that prioritizes length and angle or shape information, and through human development and supported by the combinatorial capacities of human language and other symbol systems like pictures, these complementary geometries come together and support the development of a natural geometry that captures Euclidean geometry, including eventually granting the kind of symbolic concepts that are captured by Euclid's Elements, for example, like linearity, parallelism, perpendicularity, and symmetry. And some of my work, I think, suggests that this story may capture some of what we know about the cognitive origins of geometry. And then I think there's another proposal worth considering. It is less different from the second proposal compared with how different the first proposal is to the second proposal. But here, what this proposal suggests is that the cognitive origins of abstract geometry are more rooted in these noisy and dynamic mental simulations of navigating through the physical world. And you can think about this as a random walk of a navigating animal, for example. So there's one step to the next within a representation of direction and distance. And here, the properties of how you might do this modeling are approximating Euclidean principles and grounding abstract reasoning. And consistent with the second proposal, this kind of navigation still prioritizes distance and direction. But here again, this third proposal is a little bit different insofar as it emphasizes this role of simulated navigation during abstract reasoning. And here, and I'll go through some of the experiments that I think support this proposal. But overall, the idea is that there are findings suggesting that older children and adults reason about Euclidean properties of planar figures, not with language like rules or symbolic concepts, but rather with approximate and dynamic mental simulations of figures. So if you're thinking about the general properties of a triangle, for example, you might extrapolate side and corner information and imagine a translation to that corner and side information to make judgments about what kinds of what might result in changes to the shape of a particular figure that you're given. And the idea in terms of development is that reasoning consistent with Euclidean geometry may emerge in human development when children start to reason using this mental simulation process. So this might be a really good way to get the right answer on a lot of kinds of geometry problems. And the eventual way that we develop this kind of natural geometry are with these principles inherent in the simulation that allow for an intuitive but approximate grasp of Euclidean geometry. Nevertheless, they're good enough to support learning of formal geometry, including concepts like linearity, parallelism, perpendicularity, and symmetry. But the key is that they're nevertheless still approximations. And so these three proposals have some similarities and some differences, but I think it's important to point out that they differ in their commitments to these foundational representations of physical geometry, of places and of objects as a grounding for abstract geometry. So the first proposal suggests no such grounding. There's an immediacy in the symbolic nature of abstract geometry. The second suggests grounding in both navigation and object shape recognition. And the third suggests primarily grounding in navigation. So what I'd like to do in the talk today is to go through a series of experiments in my lab that I think intervene on the debate among these options for these proposals for the cognitive origins of geometry. The first set of studies I will talk about are studies with infants that we've conducted in the lab that I think provide evidence against this first proposal, this language of thought for geometry proposal, by suggesting that there are, that in infants, they are missing some of the geometric sensitivities that are required to engage with and understand Euclidean principles. So we're going to be doing studies with infants that are looking at whether or not in their perception and discrimination of visual forms are inherent in that process Euclidean principles, or are they sensitive to different kinds of shape information instead? And the latter the sort of the middle part of the talk will discuss these next two proposals in terms of how are older children, so 6 to 12-year-old children, engaging with verbal questions in geometry that may reveal the mental processes that underlie their reasoning. So what are the mental representations and processes that are allowing them to reason incorrectly or correctly when given a question about the general properties of shapes, things that you could use Euclid to, you could call upon the principles of Euclid to answer, but the question is, are kids actually doing that? And how does that relate to mature geometric reasoning in adults? And then finally, what I will do is I will just briefly talk about some of the intervention work that I've done, taking these ideas that are everyday foundational sensitivities to the physical world, things we share with other animal species, are the grounding for our ability to understand the language and symbols of formal geometry, such that if we exercise those foundations, we will see transfer and growth in the acquisition of these concepts in a school setting. Okay, so the first set of studies is looking at how infants perceive visual forms. So there has been plenty of work over the past, at this point, 50 years, exploring what information infants can use to discriminate basic 2D shape information. Do they use angle? Do they use relative length? Can they tell the difference between a triangle and a square? And is it because of the number of sides or the angles of the corners? And we wanted to build on this tradition, but in a new way, where the questions that we asked about infants' form perception was really trying to figure out if the form information that they can discriminate is the same kind of form information that they're asked to learn about in school. So if you have an angle, for example, the way that you need to think about it if you're learning about angles in math class is that it's a scale invariant, right? So I can form a 45-degree angle with the space between my index finger and my thumb, or I can take my two arms and still form a 45-degree angle, even though that first shape is a lot smaller overall than the second shape. So do infants understand angle, for example, in a scale invariant way, in a sense invariant way, no matter what direction it's facing, in a translationally invariant way, doesn't matter if it appears on the upper left side of the screen or the lower right side of the screen. Are infants' sensitivities to shape information, are they consistent with the kinds of shape judgments that we're asking young children to learn once they encounter that in school? So we adopted this paradigm from the infant literature called the change detection paradigm. And here I'll just play an example, sort of a little schematic of what it looks like. So you have, in this case, we were testing 7-month-old infants, and infants sit on their caregiver's lap, and in front of them are two screens or a very large screen with two different sections. And on one side of the screen, what you'll present is the change of interest. So as you can see here on the left, there are triangles that are changing in shape, alternating back and forth rather rapidly. On the other side of the screen, there's also a change happening, but it's not a change in shape, it's a change in size. So we have changes happening on both sides, but the one that we're most interested in whether infants can detect is this shape change over and above any other kinds of changes in rotation, position, sense information, left, right direction, and scale. So we're sort of pitting it against another kind of change that could be salient, but in this case shouldn't matter if we're thinking about the shape information important for learning formal geometry. So again, this is the scenario in which we put infants, and we did this over 8 different experiments. And there were 16 7-month-old infants in each experiment. And on the right here, I just have a schematic of what the paradigm looked like. So the infant, again, is sitting on their caregiver. We have on their caregiver's lap. We have a size change on one side of the screen with flashing figures. And then on the other side of the screen, there is a shape change as well as a size change that comes along with the shape change. And the question is whether infants would look longer at the shape and size change displays compared with the size only change display. And this longer looking indicates a greater interest in that particular shape change that is indicative of their noticing that shape change over and above any size change. So hopefully this paradigm is clear. I will just give you a little bit of just a splash here of all of the things that we tried to control for as we created these stimuli. This is more information than you probably need, but the idea here is that we really tried to boil down the changes that were happening on either side of the screen to really just, a shape change over and above a change in size on that one stream. So I'm not sure if you can see my pointer's not working, but on the top outlined in red, all babies saw those two forms alternating with one another. And then half the babies saw those two long, skinny triangles alternating with one another on the other side of the screen. And the other half of the babies saw the two fatter triangles alternating with each other on that other side of the screen. So we could make sure that it wasn't something about having a preference for looking at a particular triangle, for example. So here's what you saw a little demo of sort of the idea of the paradigm, but here's a video that babies actually saw, and see if you think it's easy to tell which side has the shape change. Okay, so I think it's pretty straightforward. You might have noticed here that unlike what I showed you in the demo just a couple slides ago, we actually had limited orientation changes and no left-right directional changes in this first experiment. Based on other studies, we wanted to start here and see, okay, are babies even able to notice these shape changes in this kind of rapidly presented with these rapidly presented displays. So our first question is, do they notice this shape change and look longer at it in terms of global shape with limited rotational changes, no left-right flips, and some scale changes? So what I'm going to show you next are infants' looking times, the proportion looking to the shape and area change displays. Babies saw 4 60-second blocks here. So it was really a lot of time for these babies to look. There was a little break in between each block, and babies could look as much or as little as they liked for these 4 blocks. And we created a proportion for their looking time to the shape and area over the area only displays, collapsed across the 4 blocks. So what we'll see in this first experiment with triangles, global shape changes, plus or minus 30 degrees in the rotation, is that babies indeed look longer at the changes in the triangle shape over the changes in the area alone. So again, as I mentioned, we're interested in how closely their shape discrimination might reflect the kinds of Euclidean principles we're interested in terms of learning about shapes later on. So our next experiment now did this full variation of orientation and left-right direction and position. So here we were building on the first experiment to see, okay, are babies still noticing this shape change over and above the other changes that were happening at the same time? And we find that they did. In fact, notice these changes. Just like the first experiment, it didn't matter if we implemented changes in translation or orientation from 0 to 359 degrees, babies could still do this. So we thought, okay, they can do global shape changes, but we know that triangles are composed of sides of particular lengths and angles of particular sizes. Are babies using the angle information, the length information, or both types of information to discriminate these global shape changes? So our next set of experiments broke these triangles up into L-shaped figures that in the first 2 experiments are now going to test baby sensitivity to relative length information. So here's what the stimuli look like. We, on one side of the screen, showed changes in relative length. So you can see that on the right. And on the other side of the screen, we just scaled the same figure without changing any of its relative lengths. And so to me, at least, this looks a little bit harder, but the question is, can babies do it? And it turns out they can. So they are able to discriminate shape changes using relative length cues alone over and above scale changes, position changes, orientation changes, and sense changes, left-right direction. We wanted to replicate and extend this finding. Now we had done it with obtuse angles Is it also present when we show babies acute angles? So here are the stimuli here. Again, we have our scale change on the left and our relative length change on the right. And it turns out babies can do this too. So babies can discriminate global shape changes with orientation, sense, position, variation, as well as changes in relative length. We wanted to go on to ask about angle as well. So do infants perceive the angle information that can discriminate visual forms? We started with twofold change in angle as we had used a twofold change in relative length. And our first experiment used the same kind of variation in orientation, left, right direction, position, and scale. So take a look at these stimuli. So if you guys were all in front of me, I would ask you, what do you think? Do you think that babies can do it? Because to me, this seems really obvious. And it turns out, in particular, more obvious than the relative length changes. It turns out that babies actually can't do these kinds of discriminations. So when we have a twofold change in angle, and we at the same time vary orientation, left, right direction, and scale and position, babies aren't looking longer at the side of the screen where there is an angle change over and above all of these changes. We thought, okay, maybe the angle change just isn't obvious enough. Maybe they need an even bigger change in angle information. Twofold isn't enough. There isn't really a calibration between the discriminability of a twofold change in relative length versus a twofold change in angle. They're on different scales. So let's just make a bigger angle change and see if they can do that. So we tried that as well. Here are what those stimuli looked like. All right. Again, we were surprised. Babies did not look longer at the angle and the angle change side compared with the scale only change side. So we thought, okay, it's really hard to make any positive conclusions from null findings like this. Let's try one more time, make the angle change even bigger and see if babies can do that. We did. Here are those stimuli. And as you might have guessed at this point, babies still couldn't do it. So here we have evidence for these global shape, sensitivities to global shape information, relative length information, and pretty good evidence that they're not so good at angle information under these same conditions. To try to better understand this null effect in the angle experiments, we tried one more thing. We went back to these original stimuli with a twofold change in angle, and we decided that instead of allowing for the 0 to 359 rotation and the left-right flips over, above, and above the scale changes, we would go back to the parameters from the very first global shape experiment, where we limited the orientation changes at which these two shapes are presented to see if under conditions like this, where there wasn't an orientation change of the whole figure, whether babies could attend to the relative orientation between the two lines in the figures that were presented. So this is not a orientation invariant a sensitivity to angle information, but rather it's using the same angle stimuli to show that they nevertheless can discriminate these figures under certain conditions. So here's what those stimuli look like. And lo and behold, babies are able to now discriminate those shapes with the limited orientation changes. So what we concluded from the set of 8 experiments was that infants have a really a specific kind of geometric sensitivities when it comes to their discrimination of visual forms. They can discriminate globally, shape information, even under changes in orientation, left-right direction, size, and position. That global shape discrimination, however, seems to be driven by a sensitivity to the relative length only in shapes. So in the experiments probing relative length alone, we see that babies succeed in discriminating figures with all of these other changes happening at the same time. They don't, on the other hand, by contrast, discriminate changing angle information when all of these other things are varying at the same time. Only when they can discriminate forms that are changing in angle, but only when those forms are held within 0 to 30 degree orientation relative to each other. And so this suggests that baby sensitivity to angle information, as is necessary for an understanding of angle that will help your learning of formal geometry, of Euclidean geometry, isn't present in babies. And is important to keep in mind when we're trying to figure out whether or not there are any conceptual visual primitives, symbolic conceptual visual primitives that look like the primitives that Euclid uses in defining his elements. So we're building on this experiment by looking at other candidate primitives that we think might more or less capture infants' abilities. So specifically, we're looking at using this very same paradigm, whether or not babies can look longer when forms change from being parallel, so that's on the left there, from being parallel to not parallel, in non-connected lines, obviously, since they're parallel lines. And then we're looking at perpendicularity as well. So are babies able to discriminate shapes that are changing from perpendicular to not perpendicular in both non-connected figures and connected figures? And again, we're aiming to incorporate elements of our displays that are really focusing on these principles and not allowing things like spatial envelope to give away the shape feature that's changing. And this work is ongoing. So I will show you, it's being led by a doctoral student in my lab named Mohit Mukherjee. And I will show you what our parallelism stimuli look like. Take a look here. That one has a loud attention grabber. Sorry about that. So again, we have this variation in orientation, in scale, position, and the only thing that's happening on the right that's different is that the lines are going from parallel to 45 degrees. Here is a baby. I will, for the sake of time, only show you a section of this 1-minute video, but you can get a sense too of what it's like to have a baby in this experiment. And when the baby looks to the right, that means that they're looking longer at the display that you can see on the right there in the picture-in-picture. And babies have 4 minutes to look at this kind of stuff throughout the block, so they don't look the whole time. But an aggregate of their looking shows that they actually do look a good amount. And over a sample of even just 16 babies, which is rather small, you get a pretty consistent finding where most of the babies will look longer at the shape change in the sample. So I'll just skip ahead, again, for the sake of time. We have preliminary data here. We only have 14 of our 16 babies collected. But preliminarily, what we see is that babies are looking longer at the shape change, so the parallel going to 45 degrees over and above the area only change, the size change. And I think this is already significant or close to it. Again, we still need 2 more babies. It's a small difference, but it's very consistent across the babies that we test. We haven't tested the perpendicularity conditions yet, but I will show you what those look like. My prediction is that babies will be able to do the parallel condition, but not either of the two perpendicular conditions. And the reason is twofold. One, they can't do angle. So if they can't do angle in general, then that's going to include going from a 90-degree angle to a 45-degree angle. Here is perpendicularity in closed forms. Now, the possibility is that there is the special category of perpendicularity that means it's treated differently from other angles, like the other kind of arbitrary angles that we showed in babies in the other experiment. But I don't think this is the case. There's other research from Veronique Izard and Stan DeHaan and colleagues suggesting that it's not until about age 5 that perpendicularity sticks out and pops out as a geometric form worth noting among other forms. Versus parallelism, which at the youngest kids they've tested, 4 to 5 years of age, does seem to already pop out. So to briefly hop back to these proposals for the cognitive origins of geometry, the infant research, I think, intervenes on this debate insofar as it suggests that this language of thought hypothesis for geometry, in which there are early emerging abstract and symbolic Euclidean principles already present in humans uniquely, that then allow for the understanding and acquisition of Euclidean geometry in school. I think that these infant studies cast doubt on that proposal, insofar as it suggests that discrimination of angle information in the way that we understand angle in a formal definition is not present. And so it's unlikely that there are these conceptual primitives that are looking perfectly like the Euclidean primitives. And we'll see whether or not babies can do things like perpendicularity. I doubt it, as I said, but that I think will also shed some light on this debate. So now I want to move to studies with infants, to studies with older kids. And in particular, I want to start asking about what the mental representations are that underlie our conceptions of abstract geometry. So in a study I did with my colleague, Yuval Hart, who is pictured here on the right, we asked of children and adult visitors to the National Museum of Mathematics. So they're my collaborators. We do lots of outreach events, talk series, and also research with the visitors to the museum. We asked whether static figures and language like rules, the kinds of things that kids might see in their formal geometry textbooks, whether we really call upon them intuitively when we're reasoning about things like the general properties of triangles. So let me give you an example of the kinds of questions I'm talking about. So in one task in this study, we asked 7 to 12-year-old children and adults questions like these about the general properties of triangles. So we showed them the bottom 2 corners of a fragmented triangle, and we said, take this partial triangle here. What if I increase the distance between the bottom 2 corners? What's going to happen to the angle size of the top corner? Is it going to get bigger? Is it going to get smaller? Is it going to stay the same size? And so we chose these kinds of questions because they were adapted from a version of a very similar kind of experiment that had been done with DeHaan, Izard, and their colleagues in the Amazon with individuals who received no formal education in geometry, but who nevertheless, by around 10 to 12 years of age, can get these questions pretty much right. And so our question was, is there developmental change here? They couldn't look at it in their populations. And what are the particular mental strategies that folks are using to answer these questions? Do they have a kind of symbolic conception, a language-like or logic-like conception of triangles and understanding of triangles? And then they're implementing rules that they might have either learned or might have gleaned from their experience with shapes. Or are they doing a kind of mental simulation where they're extrapolating features of the triangle that's missing and then sort of reading off an answer based on their mental extrapolation? So what are the mental representations that lead older children and adults to succeed in tasks like this? Have they internalized the rules of Euclidean geometry, or were they adopting some other strategy like a dynamic mental simulation-based strategy? So the first thing that we observed is that there was a difference in older children's and adults' accuracy based on the size of the transformation we described. So whenever we said there was an increase versus a decrease to some property of the triangle, participants would take longer to answer and get more answers wrong. So what this means is that their responses were scale dependent. So even though the rule that the internal angles of a triangle sum to a constant, whether or not it's a big triangle or a small triangle, our participants were treating those two triangles differently. When they were big, they were taking a long time and they were getting more answers wrong. When they were small, they were taking less time and getting more answers right. So this was a bit of a hint to us what strategies they might be using, because the rules of Euclidean geometry are scale independent. So the idea being here that maybe they hadn't internalized those rules. So this was one clue from this one task. We also had our participants do another task where we measured their visual completion of partial triangles. So here's a great example I like to show of a younger and older child completing this task. So you're going to see different examples of triangles, and the participants are going to respond here by placing a red dot where they think the vertex, the top vertex of the triangle is. So occasionally you'll see the video freeze that indicates when children are responding to the same trial. So you can compare the responses across the 7-year-old on the left and the 11-year-old on the right. So take a look. Okay, so as hopefully you saw, the 11-year-old is more accurate. And so given the scale dependence we saw in the verbal reasoning task, we wanted to figure out if this visual completion process for individual children was related to their success in reasoning about the general properties of triangles, suggesting that they were doing a kind of mental version of this process when they were doing the verbal reasoning problems. So the better they are at completing the triangles visually, is that related to their explicit reasoning about the general properties of triangles? And what we found here, what I'm going to show you, is the relation between that visual completion process, so how good they were at completing triangles, just asked to click the top corner, and their performance on the verbal reasoning questions. And this is split by 2 different age groups. We have kids younger than 10 who are not reasoning in a way that's consistent with Euclidean geometry, and kids who are older than 10 who are reasoning in a way that's consistent with Euclidean geometry. The idea being that the younger kids are, their visual completion is not what they're calling upon in context of verbal reasoning. And so it should have no relation to their verbal explicit reasoning should have no relation to their visual completion. Versus the older kids are using this strategy when they are doing the explicit reasoning. They're using the visual completion strategy in their head when they're doing the verbal reasoning. So it should be related there. And so, as you can see, as I might have suggested, below age 10 years, when reasoning is inconsistent with Euclidean geometry and visual completion is not as good, there's no relation. But children age 10 and older, in those kids, there is a significant relation. And we also tested a group of adults on these same tasks, and there's a significant relation across the reasoning and visual completion tasks in the adults we tested as well. So I think these results suggest that geometric reasoning consistent with Euclidean geometry may not be rule-like or even perfectly Euclidean. Instead, there are these noisy and dynamic mental simulations, kind of like a random walk of a navigating animal. This is how we modeled that process, that may approximate Euclidean principles and ground abstract geometric reasoning. So if abstract geometry is not perfectly Euclidean, maybe this geometry is flexible to non-Euclidean surfaces, especially if questions are framed as judgments about a navigating agent. So in another study in my lab, which was run by Holly Huey, who was a lab manager at the time, now she's a PhD student at UCSD, and Matthew Jordan, who was a visiting Rhodes Scholar in math in my lab, for a summer. We asked whether kids and adults could make successful judgments about the most efficient path between 2 points critically on spheres. So spherical geometry is not typically taught in school, and evidence from studies with humans and non-human animals, however, suggests that flexibility beyond planar contexts, this happens in the context of navigation, including using things like slopes, curvatures, and wormholes. So it was possible, we thought, that even though these are going to be young kids, 6 to 8-year-old kids, that recognition of the shortest path between 2 points on a non-planar surface might be present in human judgments about navigation on non-planar surfaces. So we showed 6 to 8-year-old kids and adults paths between 2 points on 2D pictures of spheres, which we described as really large basketballs, and asked them to judge which path was the most efficient for an actor to get from her starting point to a goal object. So in one kind of trial, the 2 paths looked curved in the pictures, and the correct shortest path is shown here on the right. And in another kind of trial, the correct curved-looking path, now shown on the left, was paired with an incorrect straight-looking path. So if participants were insensitive to this efficiency on pictures of 3D spheres and focused only on the 2D properties of the paths, that is, whether they looked curved or looked like curves or looked like lines, they should answer at chance in this first kind of trial and below chance in the second kind of trial. So what I'm going to show you here are participants' choice of each kind of path in the 2 trial types. And taller blue bars mean that, that the correct answer outlined in blue was chosen more often, and chance is 50%. So although children often chose incorrect paths that looked like straight lines, they were surprisingly successful at identifying paths when comparing 2 that were curved. And adults performed above chance in both kinds of trials. So the idea here is that children's intuitions about the shortest paths between 2 points may be flexible to spherical surfaces, at least when judgments are couched in judgments about efficient navigation. In fact, we may have intuitions underlying our understanding of non-planar formal geometries, as well as Euclidean planar geometry. So we didn't have a condition here that contrasted a navigational framing with any other kind of framing. So something like a representations of objects, for example. This was just a prompt about a navigator. But the next couple of studies I'm going to show you, we do. And so the idea is to figure out if we're comparing couching questions as navigation problems versus object recognition problems, are we getting a focus on different kinds of geometry? And so the you now might be able, might be getting a sense that I'm sort of advocating for this third proposal, this idea that noisy and dynamic mental simulations of navigating the physical world are approximating Euclidean principles and grounding our abstract reasoning when we get verbal questions about the properties of shapes. And so we wanted to sort of put this to the test by directly comparing linguistic descriptions of places and objects and abstract points and lines to see what kinds of geometry people were thinking about when seeing just really basic visual forms. What does this language evoke in terms of the geometry? So this is a project led by a postdoc in my lab named E. Lin. And what we did is we showed adult participants a bunch of trials with simple visual animations like this. And I'll just talk over while this is playing. It's super simple. The idea is that adults were randomly assigned to one of 5 conditions, which created different spatial contexts. And we asked people to provide a mouse click response. And they were asked to either click anywhere, complete the triangle, where the next corner of an object would be, where the next stop on an agent's path would be, or where the next point on an abstract plane would be. And we aligned people's responses. Here is sort of the variation that we showed in terms of where we asked them to click next. They saw all of these different kinds of trials. And the question was, where would they click next? So here are the results. And I want to focus just, again, for the sake of time, I realize that we're already at the end, almost close to the end of the hour. I want to focus on the object navigation and abstract conditions. So unique responses in the object condition clustered opposite the given figure's first visible point, as if participants were preserving the overall shape of a closed figure to form the third side of what would be a parallelogram. Unique responses in the navigation condition, in contrast, clustered past the end of the given figure's second visible point, as if participants were continuing the paths, an agent's path with the same distance and direction. to create an open zigzag figure. And despite the identical visual stimuli and the minimally different linguistic descriptions across conditions, participants produced very different responses, as you can see. But in the abstract condition, you'll see actually that the responses look a lot like the navigation condition. So there was a large cluster of responses extending beyond the given figure's second point. So we replicated and extended this. Instead of allowing participants one click, we gave them unlimited clicks. And we saw the same pattern emerge. I'm going to show you heat maps here of these responses, again, focusing on the differences across conditions. And what you'll see is there's a similarity between the navigation and abstract conditions shown on the bottom of each experiment's plot here, where what you're seeing are the colors indicate differences between the conditions, and there are no differences indicated really, or just tiny spots of differences indicated between navigation and abstract, whereas object and navigation and object and abstract do show regions of difference. So the suggestion that we want to make here is, as we are sort of wandering the abstract world of Euclidean geometry, we might be doing it as we wander the physical world of everyday life. And again, for the sake of time, I want to just skip ahead to what kinds of implications this might have for teaching and learning. So the suggestion here from this work is that these foundational spatial concepts of places and objects, they persist into adulthood even after we learn about geometry in school. And there is an intimate link between the intuitions we have about abstract geometry and the geometric intuitions we call upon in contexts of navigation. So in addition to informing philosophical debates about the origins of geometry, I think these findings have implications for the design of math pedagogies, like some that I've tested in large-scale randomized controlled trials. So I'll just briefly tell you about sort of the aim of that work. So I worked with a collaborative team to field test school readiness curricula in mathematics that focused on this idea that there are foundational abilities in the numerical and spatial domains that are shared with other animal species, that are universal among humans, and that form the foundation of our uniquely human capacity for learning the language and symbols of formal math. And what we did is we worked together as a team of economists and psychologists. Economists led by the team was led by Esther Duflo, who's a recent Nobel Prize winner, and we there were a bunch of preschools in New Delhi, India, that were offering universal access to preschool for the community members, but they didn't have a math curriculum. And so it was, so we were tasked with designing a curriculum based on these principles that we were exploring. And we provided a set of games to these kids, math games designed based on these principles, an active control condition with social games, and then a regular curriculum. Again, it wasn't really fully fleshed out, but the education NGO we worked with, Pratham, was also presenting numerical and shape information in the everyday classrooms. We had an 18-month study where we had a baseline assessment, the games, an end line, second end line 6 months later, and then a third line, end line 6 months after that, where kids had been away from the games for a year and finished their first year of primary school. And in short, what I'm going to show you here is that we found that training and exercising these, physical foundational capacities we have in space and in number led to improvements in kids' intuitive skills. So approximating the number of dots or discriminating shapes without needing to know numbers and shape number symbols and shape names, as well as the simultaneous learning of symbolic number and shape vocabulary. So our math group here is shown in blue, and these two, the active control in red, is compared to the no treatment control, which is shown on the x-axis. So up to 3 months after the intervention, there were these improvements. On the long term, a year after the intervention ended, the intuitive skills persisted in their improvement, but the formal skills saw no long-term transfer. This suggested to us that maybe we want to incorporate the symbols and language of of math into the intervention itself. And that's what we did in the second intervention. And just for the sake of time, I'll show you those data as well. So here we had a group that in green who had combined content in their training. So intuitive, numerical arrays and shape arrays, as well as symbolic content. And on the long term, a year after the intervention, that group did the best in both intuitive and formal skills in terms of math. So just to wrap up, what I want to suggest is that, my computer froze. Okay, here we go. That it should be no surprise to us that our abstract thought doesn't come out of nowhere, but it's grounded in something. The abstract thought of our formal mathematics is grounded in the abstract thought we've inherited through evolution. That thought that has certain principles that can describe the physical scenes and objects that we interact with and other animals interact with in everyday life. And this evolutionarily inherited cognition allows us to understand the places and objects of the everyday world, but also as we wander our imaginations across the abstract planes of formal geometry, it supports our wandering there just like it does in the grounds of everyday life. Our abstract thoughts rooted in a cognition that evolution gave us to survive in the physical world, but also allows us to thrive in abstract worlds we create or imagine as teachers or as students. Thank you.
Thank you so much. Thank you. I think we're out of time, but maybe if there's time for one or two questions, if you have time, I think we can. Sorry, it doesn't. Let me try switching the mic.
I see some questions in the Q&A. Should I answer those?
Sorry, go ahead.
Okay, for the first experiment, the question is, am I sure that the changes in the features are perceptually discriminable for the infants? For example, a change in size might not be perceptually noticeable, whereas a small change in parallelism could be. Thank you for that question. We looked at previous, there's a ton of research on infant shape discrimination. And we looked to that research to try to inform our stimuli design based on principles like this. And it turns out that we met or exceeded in all of our angle experiments, in all of our experiments in that first set of studies, the area change that is discriminable by babies. I think it's something like they can do 1.5 times the area of a shape is noticeable to them. So yes, all of these features were important for us to control, and we counted on existing literature to tell us what were the thresholds that would have been discriminable had they been changed in isolation, not with all of these other things happening at the same time. Okay. Do I have any suggestions for a computational mechanism that can convert non-symbolic math capacities into symbolic capacities? Yeah. So I think that the idea is that we have dissociable systems for distance and direction for navigation, and length and angle, or length and some sort of shape kind of thing for objects, and that these two start to talk to one another. If I had to formalize this, I would think about it as a combinatorial process that happens in language, kind of like a merge operation. Chomsky suggests this kind of thing, that the combinatorial properties of language, and maybe you could formalize it through this idea of merge, is allowing for this generative, productive use of geometry that counts on these perceptual features, these kind of abstract perceptual features like distance and direction and shape information, and brings them together to allow distance, direction, shape to all speak to one another, to there be a conduit between what are potentially two encapsulated sets of geometric sensitivities. Computationally implementing merge, I'm not sure if any of the linguists have done that or the computational linguists have done it, but I think if I were to formalize it, that's what I would suggest. I think there is so the follow-up was, do I think there's a kind of language of thought mechanism? I think it's language. I think that it's the same. I think there's language, and I don't think that there are multiple language of thought systems. And I think that's different from what some other folks think. So Dehaan and colleagues, for example, think there's a specific language of thought for geometry that controls all those combinatorial operations. I think it is language that's doing it. Okay. And there's been a talk of decreased educational performance in male students in the US for a while now. The infants, so we had 128 infants participate in the first experiment, and 64 of them were girls. So we had half girls and half boys for the first set of infant experiments. And we did look for gender differences in our sample, and we did not find any. So the girls and boys seem to be equally good at discriminating the visual features of the shapes. Let's see. Would you expect differences? Okay. That said, so I've done a lot of work and looked for gender differences emerging and sex differences emerging in my studies. This is important in terms of development, and we don't find any sex differences until about I think it's 10. So we're in the study I showed you with the triangle completion, we do see boys doing better than girls in the verbal reasoning questions. And this is a lot later, I think, than a lot of other research finds sex differences start to emerge. And in the younger studies, at least I think that the kinds of ways that we're asking kids questions, we're really focusing on an ability to use one type of information. And when you're focusing on just one type of information, relative length versus size, for example, you're not going to see as many of these differences emerge. When we got to the verbal reasoning questions, there are different ways you could answer the question, different strategies you could adopt. And here is where I think there's the potential for gender differences to emerge, where there are different ways you could answer a question, and maybe you're better at accessing one way over another. And these play into people's strengths or not, and those strengths may differ based on gender lines. But we found that when we have a specific experiment focusing on, like, can you do it with relative length, we don't have differences in gender. I think all of the questions have disappeared from the Q&A. But maybe that's because folks have disappeared.
I think so. If I can, I'll ask one last question and then we'll wrap up.
Sure.
In the language of thought work you're talking about, I think in some of Dehaan's work, the language that they're talking about, I think, is sort of navigational. It's like a computational language, like Logo that involves like moving and turning. So is there something connecting those? I mean, maybe some of the work is not like that, but it seems like the language could be navigational. So what do you think about that?
I think that, yes. I think, though, that the content of the geometric primitives is, they don't necessarily talk about an origin of that content. So where is an understanding of perpendicularity coming from, right? And so where the combination in that language and thought, that combinatorial process may have some elements that resemble navigation, like turning, or kind of, something like that. I'm talking more about where does the content come from in those original primitives, right? And I think that could have navigational components, or it can also have components from form analysis, maybe a merging of the two. I have some preliminary data using that last task, that point and click task with kids. And I didn't quite get to it today, but the preliminary data is suggesting that whereas the adults might be heavily relying on navigation, the kids seem to be going through this developmental process where they're doing both object recognition and navigation. So the abstract condition looks like a mix between the object condition and the navigation condition, not solely like the navigation condition. So yeah, I'm really interested in where the content of those primitives, as they might call them, comes from. And but it is interesting to think about how the navigation component is nevertheless still part of the combinatorial process of putting those primitives together.
Great. Well, thank you so much. I think it was a very fascinating talk with quite surprising results. So thank you for sharing your work. And I know many people had to leave, but I think they were very interested in the talk. And thank you.
Well, thank you very much, and have a great rest of the term.
Take care.
Bye-bye.